instance, the subspaces of R, or rather R2. What are the subspaces of R2? Well, this we saw. It can, since R2 is two-dimensional, we can have either a zero-dimensional subspace, which is the trivial one, the zero space, which contains only 0, 0, or any line, okay, and where M can take, I'm writing very loosely, M can take any real number or plus infinity as a value, and R2. So, for instance, Lm, so Lm means the line with slope M. This is an indexed family of subspaces of R2 indexed by the reals. You could have many others. I mean to say for R3 you could have many others and so on. Okay? So, to be actually very pedantic, one should write this set as okay, or even one could write this as another way is.
So I didn't get that.
Yeah, this is a better way.
Oh, okay.
Sorry. Where you remember I defined the LMs. LM is this or the x-axis.
Oh, okay.
The x-axis is points like say x0. This itself is the subspace. So, okay. So these are all the subspaces of R2, and so we have a indexed family there. So, for instance, one could ask, what is the intersection M in rationals of LM? Okay? So, such questions we have seen. All right? Next, or let's start today's class.
Thank you, sir.
So regarding today, let's go back. Let's go back. Last time I was a little bit fast, but let's go back to the Gauss-Jordan algorithm. Okay? So, my goal today is to convince you that the Gauss-Jordan algorithm is nothing else. You remember, you have a matrix, right? you have an n cross n matrix, okay? And that you do some reductions and some operations are done, and finally it comes to a nice echelon. Where is that? To some nice echelon or a row echelon form. Or a echelon or a reduced echelon form. Whatever. Okay? And this is the key of our solving equations. Okay? So let's see why. Now, by the way, the name echelon, as you could have seen in my notes that I have sent you, is actually taken from military. It is actually a formation of the army while attacked. So it looks something like this. Okay? So as if these are my ones and the rest are zeros. Okay, you think of the matrix in that way. Okay, so that is my echelon whole story. Okay, I'll come back to it. But what I want to convince you is this. So A being a matrix, say an M cross N matrix. So it is actually a linear transformation from Rn. Why I am taking Rn? It is from an n-dimensional vector space to an m-dimensional vector space. And any n-dimensional vector space is isomorphic as a vector space to Rn. So it suffices to look into Rn only. Okay? What I am trying to say is this reduction that you are doing induces a change of base. So this is my identity map, and this is the identity map. If I started off with a basis, say C over here, I go to a basis C prime, I do again, I go to a basis C double prime. So each one of these transformations induce a transformation on Rn, that means via change of basis. And finally, it comes to a stage where basis, say, let me say C final or whatever. So essentially, if you compose this, if you do, there's finitely many steps. If you compose this, you get back only F, but the matrix representation has changed, right? The original A was the matrix representation here. So F A was this. But then you have multiplied it by such things. So that means you have multiplied A by the change of base from C to C prime, then by the change of base from C prime to C double prime, and so on. So finally you come to this C final as I wrote. So this is the matrix. Okay? And I will show that any M cross N matrix finally gets reduced to this, to a matrix like this. That's my first step. Okay? Now, since these are change of base matrices, they are bijective. Right? So you can immediately see that if you wanted to solve fx equals b, which actually means that you want to find a solution to this matrix equation, is the same thing if I call this big p's, multiplication of these p's as p, capital P. So this is true if and only if this is true. Yeah? And this being a very, very simple matrix, we will then see that we can immediately solve equations like this. Okay? So first let us attack this problem of why do I say it is a simple matrix. Okay? So, what is a Echelon matrix? By the way, before I go any further, let me introduce this notation. For Rn, I will have a basis which I will write as U in this way, U with n in brackets on the top to show that it is for Rn, and it consists, so it's a basis. It is often called the standard basis. Okay, and what is well, this is 0, 0 everywhere except 1 in the ith place.
The U represent the I identity.
Which one?
I'm saying that the U represent the I identity.
No. Remember, a basis is a list. So it's a list of vectors. So this is often called the standard basis. Okay? If I don't specify any basis in particular, then I'm considering the standard basis for Rn. Okay? Clear? Okay. Now let's, what is an Echelon matrix? So that's, as we agreed, write it in. Is a matrix such that is a matrix, let me write this. Each row, it's either a row of zeros, okay? For each I, the first non-zero entry often called the leading entry. And the J column for this leading entry is its position. Okay? So the first non-zero entry is always 1. Okay? If okay, where the leading entries and I then so it means that the leading entry, the position of a leading entry below level will be on the right, okay, and if Aij be the leading entry, then Aik is 0 for all k's greater than for all A in that column. Please close the microphone. I think it is this one is. Please close your microphone.
Western Cape.
That means
Thank you.
so below a leading entry, in that column, everything is 0. Okay? And a row of zeros. Okay? So it has to satisfy these four conditions. It is reduced echelon matrix provided you replace this. So let me put a separate color. So if you replace this by so everything in that column, okay, is 0, then you shall call it a reduced echelon matrix. Okay? That's the only difference. Reduced or row reduced or whatever. Okay? Yeah.
It can be any number, but below the zeros it can be.
Below the 1,
Can be zeros.
it must be zeros. That's the reduced echelon. Oh, I'm sorry, that's the echelon. For the reduced, above the 1s are also zeros.
Zeros. Oh.
Okay? So for instance, any upper triangular matrix is echelon. Right? But may not be reduced. But for instance, the identity matrix is a row reduced echelon mark. Okay? Alright. So now let's have an example.
Sir,
Yes?
can I please ask about the echelon matrix?
Yes?
Isn't the echelon matrix, like it doesn't, like the leading entries don't specifically have to be 1, they can be any non-zero number?
Yes, you can. Some people still like that. But since we are working with reals, we can actually reduce it further by making those ones. So I prefer to keep an echelon matrix in which the leading entry must be 1.
Okay. Thank you, sir.
Excuse me, sir.
Yes? Yes?
We have lost live coverage from PMP.
You are?
I just want to check if it's PMP's problem or your problem on that side, because I can hear you, but the visuals are not there, only the sound.
Do you have anyone to help you there?
Yes.
Please ask him, or else if he cannot, then he can contact Thabo over here. Is this an echelon form? Is this an echelon form? Why?
Third row, second column, this one.
First, no, because this is the leading entry. Over here, it is not So, if we actually replace R2 by 1/3 of it, then we come to something like this. Right? Now, is it still in echelon form? Why? Yes, because of this. Yes? So, we replace R3 by Is it still in echelon form? No. So what is the problem? Which one? Yes. So you have to again this is the final echelon form, but it is not completely row reduced, it is just echelon. Okay?
Can you change I thought?
No, we don't exchange columns. Okay? And the reason is pretty obvious. Because linear transformations come up via multiplication of a matrix with a vector, right? Changing a column, interchanging a column means say if you interchange the second and the third column, that means you have interchanged x2 and x3. So you have to be careful. Okay? No changing of columns. Columns cannot be interchanged.
Excuse me, sir.
Yes.
On the row echelon form, the leading ones, are we looking at rows or are we looking at columns?
Rows.
Okay. So in other words, the first non-zero is supposed to be a 1.
The first non-zero must be a 1, yes. Each
okay.
row.
Okay.
Okay. So this is still not completely row reduced. The row reduced version of this is
Sir?
1 minute.
Is it,
So there are few operations that you have to do, and then you get this row reduced. Yes. Yes. What is it?
What's time?
Yeah.
please close your microphone.
It's the Western Cape guys. The Western Cape guys, can they switch
I
off
think
their
it's
phone?
George. I think it's George.
Yeah, it's WC George, Western Cape.
I didn't even bring my cell phone. So, this one, let us give this matrix a name to say it's an echelon matrix and say, okay? Now, my purpose would be to show that first, let's look into these different matrices.
Excuse me, sir.
Yes.
Can you please remind me again, for row reduced, what's the condition to have a row reduced?
To make it row reduced, to make it echelon, you need, if this is the leading entry, everything below it must be 0. To make it row reduced, everything in this column other than this leading entry must be 0. That
Okay.
means this 2 has also to be made 0.
The two what?
That 2 on top of 1,
Okay.
this 1, 2 position, this also has to be made 0. Okay? So over here you have 1 row operation, and for the last column you have 2 row operations to make it. So 3 more
Okay.
row operations will make it a reduced one.
Okay, I get the row echelon form, the leading ones, in other words, the first non-zero element must be 1.
Yes.
Now, for row reduced, what's the special condition? Like, I'm just trying to...
Yeah. Say for instance, this is the leading row. This is the leading element in the second row. To make it row reduced,
sorry, sir, I'm unable to see where you're pointing at.
this member, the 2 member in A red,
Yeah, I'm saying I'm not able to see where you're pointing. Which matrix are you pointing at?
A red.
Okay.
So the 2 member, that's the leading entry. And in the second column, everything is 0, other than that leading entry.
Yes.
Okay, but here, in the A-ish matrix, the 2 member is the leading entry for the second row, but there is this 1, 2 entry which is non-zero.
Okay.
So in echelon, we don't demand things above the leading entry to be 0.
Okay.
We only demand things below the leading entry to be 0.
Okay.
So in row reduced means I need things above and below to be 0.
Okay.
Sir,
Okay. Yeah?
sir, can I please ask how did we get from the echelon form to the reduced echelon form?
So for instance, in the second column, this 2 has to be made to be 0. So you replace R1 by R1 minus 2 times R2. Right?
So wouldn't the last entry on the first row have to be -3?
Yes, it will be. It will change. It will therefore change. But whatever it changes to, still then, it will be something non-zero possibly, or it could get to 0. If it is a 0, it's fine. But here in this case, it will get to -3, right?
Yes, sir.
And then, for the fourth column, you have to replace R1 again by R3 plus, R1 plus 3 times R3. And R2 so these three operations will make it reduced. Okay? So that is mine. So finally you will get it in this reduced form.
So I just want to know, for, say for example, in our second column, instead of having a 1, say by the leading one, instead of having a 1, we have a 3 or 4. Do we have to reduce it down to a 1?
Yes. That is the definition of an echelon matrix. Okay? The first leading entry must be 1. Okay? Alright. Now.
Oh, so can I please ask the last question?
Yes?
Does the last column also have to be a set of zeros? Like 0, 0, 1, 0, 0, 0?
Yes, yes, yes. There is only, in the last column, there is one leading entry.
Okay, thank you, sir. So is this an augmented form or is it a matrix of
This
coefficients?
is a matrix. I have not done anything like augmented things. This is just a matrix.
So is it a matrix of coefficients or is it
I
augmented
didn't say
matrix?
anything. It's a matrix. I'm coming to it now.
Oh, okay.
So now, let's check. So can you please tell me what is this? Because A was this. Then what was the second column?
0.
Yeah?
Which one?
For A to start. Yes, 2. 2.
3, 1, 0, 0.
Then?
Then 0, 0, 0, 0.
Then?
1, 6, 3.
1.
6, 3. 4, 0.
0.
4, 4, 4.
So this is one matrix. Then it was, this was 2, right?
Yes.
2, 1,
And then it was
1, 2, 1, 0, 0.
1, 2, 1. This was the Echelon matrix. And so this A represents a linear transformation from where to where? Yes, this A represents a linear transformation. So from where to where? I said A represents a linear transformation. So what is the domain vector space? What is the codomain vector space?
But isn't the domain 4 R4 and the codomain is R5, 1, 5?
Correct. Correct. Okay?
So how is it R5?
What is the order of this matrix? What is the order of this matrix?
Okay.
So this is also a linear transformation from R4 to R5. And so also is this. Now so this, the matrix, because this is a 4 cross 5 cross 4 order matrix.
Then you are saying that we are transforming R4
R4 to R5. This was actually done again and again when I was describing what is the matrix of a linear transformation. And the way I was doing it, it was very, very clear that this has to be. Because, now let's do it again. So now what do I mean by that this A represents this? Well, what is this? The linear transformation part is very clear. This is just multiplication by A. Here also it's true. It's multiplication by A. But what do I mean by this F is being represented by A? It means that the matrix of F is A. When I didn't say anything, so I meant matrix with respect to the standard basis. Okay? Right? Now let's see. So it is telling me that, remember that was one of my very, very strong propositions, how to construct linear transformations from finite dimensional vector spaces. You just tell me, it is enough to know what is its values on the points on the basis vectors. Good. So now U4 has 4 basis vectors. Tell me now, what is F at this? Let me write a little more. So tell me now, what is F?
Sir?
Yes?
Does E14 mean
1000?
Oh, it means the first column in the fourth dimension.
Yes.
Isn't it in the fifth dimension?
F of E14 is in the fifth dimension, correct? And that is its coordinates with respect to the usual basis is this. So this is exactly E1 goes to E1. Okay? and E2, that's its coordinates here. Well, you immediately know E3 goes to 0. And E4 goes to this one.
Excuse me, sir.
Yes.
For E1, why are you writing E1 subscript 5?
Superscript.
Yeah.
Remember, E15 is the first basis vector in the standard basis of R5. And what is that?
Okay,
That
1
is
0.
first coordinate. Yes, 1 0 0 0.
Okay.
Okay?
So which means, if you write it this way, you can write 1 0 0 0 0.
Yes. That was my convention that members of Rn, when considered as a matrix, I'll always consider it as a column matrix. Okay? Now, so you see.
Excuse me, sir.
Yeah.
Can you please explain, because you have f of E1 4 equals to E1 5. Is that so what is f of E1 4?
Well, you know that this is, you told me just now. You told me this one.
Yes, I know. I'm just asking you, because when you say f of E1 4, what exactly are you talking about there on the left-hand side?
Yes. The linear transformation f takes E1, the first element of the basis in U4, to this thing, to the first, to E1 5.
Okay. No, I think I see it. I see. So basically, that's a linear transformation.
Yes, that's the linear. See, I'm building up on what I have said.
Yeah.
To tell me a linear transformation, it is enough and exactly enough to tell me what does its values at the basis elements. If I know the values at the basis elements, I know the linear transformation. And that's how I actually construct the matrix. So, the corresponding matrix. So all these things are very, very interconnected. Give me a matrix, I know what the linear transformation is. Give me the linear transformation, I know what the matrix is.
Okay.
And you see, from here, you immediately conclude that this belongs to the kernel of f. But you still don't know what the kernel of f is. Okay? You still don't know what the kernel of f is. Correct? I'll come back. But let's see what is the beauty of this echelon or reduced echelon. For instance, over here, if I do the same trick, I know this goes to this. I know that is E3. So the reduced echelon immediately tells me, that it tells me from here that the range, that the image has dimension 3, and therefore the kernel has dimension 1. The dimension of the image plus the dimension of the kernel is dimension of the domain. Okay? So, you see, over here it is also equally simple, but you have to do a little more. So, for instance, you know over here, sorry, 2 zeros. Okay? Yes.
For the reduced Echelon form, there is the dimension of the image and the dimension of the Canon form, of the Canon H rather. It's the domain.
Is the dimension of the domain.
Dimension of the domain.
Yeah? So from here I know. So doing the reduced echelon tells me immediately what the rank and what the rank of the matrix is, what the kernel of that matrix is. It tells me that the kernel is completely determined by the span. It also tells me what the kernel is here. Okay? It tells me completely what the kernel is. Not only its dimension, it tells me what the kernel is, and hence also tells me what the image is. Okay? So you see, doing this exercise tells us that looking into a matrix as such, well, in general linear transformation is good, but looking into its reduced version is much better. We can immediately use it to solve things, to say much more about this linear transformation. It gives us much more handle. Okay? So now so now, the next first thing that I need to assert or show that every matrix can really be transformed into a row-reduced matrix. Okay? So, the question is, and the answer is yes.
No. I'm saying no. There are those that have the zeros of there are those that can be infinity solutions. So
there can be linear systems which doesn't have a solution. But my question is different. Can every matrix be reduced to a row-reduced form?
Yes, I'm going to answer the question by using the contrary to what the question is asked now. I'm answering the question by saying that Yeah, those questions, when we try to choose them, we find that the initial chain or when the user chain or when you work with them, get up there at the end of the
Yes, but what do you mean by a solution of a matrix?
Me, I don't know in that case.
Right? So, what you are speaking, yes, when I have linear systems of equations, I will come back there. But I'm saying, for a matrix, if you just give me a matrix, what does it mean to have a solution of the matrix? Right? So I'm saying every matrix can be converted, transformed to a row-reduced one. And here is the algorithm. So you start off, I'm trying to describe the algorithm, and I leave it to you to complete it. So what do? You start off on the first row. Suppose the first 1 entry is non-zero. Okay? So let's say AII, those entries are the diagonal entries. Okay? Suppose AII entry is non-zero. Okay? So A11 is non-zero. Then I divide that row by A11. Okay? Replace R1 by okay? And you have to make everything below this to be zero. Right? So you replace the ith row then by the ith row minus AI1 times R1. Right? Remember, after this step, your first entry is 1. So when you multiply it by AI1, this entry becomes, so what you had over here, this non-zero, this entry, you multiply by this, these two entries become same, you cancel this, and that's how you're doing the ith row. Okay? So the moment you find a diagonal element, which we often call the pivotal element, that is 0, you are kind of done. You can actually reduce that column. Okay? So next you go, yes.
Can we please go back to the previous slide?
Yes.
Sir, I'm very, I don't know what E14 means.
Well, here is it. So E14 clear? Still not clear?
Sir, I'm so confused.
See, E14 is a vector from R4, so it must have 4 coordinates. Its first coordinate is 1 and the rest are 0.
Oh, oh my gosh, is it that thing in standard basis?
Yes.
Oh, okay, I understand. Oh, I understand. Thank you, sir.
Okay. So, there is a problem with it. If a pivotal element is non-zero, you can reduce everything below it. And similarly, you can reduce everything above if you want to make row reduce. Okay? Good. What happens if the pivotal element is 0? So then, if this pivotal element is 0, then your next search, which one do you exchange with? That is which is non-zero. So you go down and look for a non-zero element. So, then check if some in which case interchange
that the fifth column is all 0?
Maybe. That's what I'm saying. So if not, first column
then what happens if that the best software is 0 and I will use as the next column that will be
coming. Wait. Coming. Right? So suppose you have this whole first column as a column of zeros. Now what do you do? So the leading entry over here in the first row is not here. So you have to go and search here. Okay? So suppose if you find something over here to be 0. Okay? If then you should start, this is your first leading entry. First row, first leading entry. Okay? So, you should start now thinking, so you can reduce all the columns over here, everything. That means, you don't interchange, but you reduce it. But then, to make it row reduced, it must be there. If this is the first time when you have a non-zero one, then after that you have made everything 0 over here. The next leading entry cannot be here. Okay? So that you have to keep in mind. Okay? So a check is obviously to check whether everything over here is 0. If everything in between is 0, then you are well and good. You are in proper line. You can then go to the next element here. If not, be careful now. Possibly this one is non-empty. Okay? Okay, if it is non-empty, go reduce everything below. And go on and on finding all the non-empty things. Okay? Yes, go on and on because, say suppose there were 3 columns over here. and everything over here is 0. Okay? Now, this one must be only over here. So you have to, at this stage, you'll have to interchange this first row and this row. Okay? So that you make that requirement that the leading entries are all in that echelon form. Okay? Alright? At that stage you'll have to do it. You have to interchange the rows, and so you see, this settles this issue for the first one. Okay? And in doing so, we have actually obtained a reduction up to this stage. Okay? One minute. Well, if this is all of the matrix, then fine. If not, go to the next one. Next column. So next column, one row below. Okay? And then replace things that was your first entry, like 1, 1. And start again. Right? Start again to do the same thing. So that's this way, this algorithm goes on and on and on until you come to the end. And you know there are mn steps at most. If this is an m cross n matrix, there are at most mn steps in which you'll have to iterate and you will stop. Okay? So this algorithm actually tells you that every matrix can be reduced to an echelon matrix or a row reduced echelon matrix. Okay? And then I'll come back to it. What are the operations, row operations? Yes. So the simplest one is interchange two rows. Okay? Multiply
add two rows or something.
So replace
and then I'm asking if I'm asking for certain node or node. Can I divide the matrix in the form of operation?
in the
Can one division as one of the operations?
good and coming to it. Let's see. Okay? So now, let's try. Let's take a 3 by 3 case. Or let's take a 3 by 2 matrix. Or 3 by 4 matrix. Okay? I want to change the first and the third row. What do I do?
When I say one interchange with
Yes. Can I do it by matrix multiplication? Why? Think. So this is a 3 by 4 matrix. Okay? I want a matrix over here by which if I multiply, I would get, the answer would be right? Okay, so this is also a 3 by 4 matrix. So therefore, this matrix has to be a 3 by 3 matrix. Okay, now it's this times this plus this times this plus this times this. Since this has to be x, this must be 0, 0, 1. Let's see about this. This way, this becomes y. This becomes z. This becomes t.
Okay.
To make this a, this must be 1, 0, 0.
The second one has to be 1, 0.
0, 1, 0, good. That's it.
Which means the mean diagonal, you will make it the index of the I one, the I.
Well, in this case, it turned out to be so, but in other cases it will not be. But let's see. This is a matrix. Okay? So it's a linear transformation. This matrix induces a linear transformation from R3 to R3. Okay? Good. To give me this linear transformation, it is enough. So I want to say this linear transformation, I want to find the linear transformation whose matrix is this. Okay? So it's enough to tell me where the basis vectors go. So where does E13 go? Where does E23 go? And where does E33 go? With respect to the usual, so you have taken the usual basis on both sides. Okay? So you see, is it clear? This one is? So it is? This 001 is? E3. So E1 goes to E2 doesn't change. And E3 goes to E1.
So on the right hand side is the transformation of...
Correct. So interchanging. This is the same thing as changing as a base change. Okay? You interchange the ith and jth basis vector. That is the meaning of, so that's the, and this is the change of base matrix for that. So so this is quite interesting, right? You multiply on the left by the change of base matrix, and what is happening then? Well, this is actually this is actually this matrix is represented by this. Or this matrix represents this linear transformation. Okay? And then, so here you had the basis U3, and you have taken the basis U4. Okay? And then you have taken this linear transformation, which is identity, but you have changed the basis. Sorry? You have changed the basis to okay? Clear? So, the matrix for this composed, so what happens? The matrix for this, so this product turns out to be the matrix of F This is not what? This is identity composed F, right? But then our matrix, on the terms of matrix, is the matrix for this to this, times the matrix from this to this. Matrix from this to this is this, change of basis matrix, and, yeah?
See the matrix of the first.
Remember, we'll be using this very, very much. Say a basis over here is A, the basis is B, and basis is C. The matrix from A to C of G composed F, remember what is it? It is matrix from B to C, G, times the matrix from A to B of F. Right? So this F that I am writing is actually identity of, this F is identity of R3 composed F. So the matrix of this composition with respect to this and this interchanged basis. Okay? What will it be? It will be the matrix from here to here of it. It will be, matrix from U3 to this one bit. Matrix of the identity from U3 to this times matrix of it from U4 to this. But that is exactly this change of basis times the old one.
I see it now.
Yeah? Yes?
Can you just please explain that, what you just explained, this transformation, because I missed the lecture on Tuesday, so I'm trying to, I think there's a gap in my knowledge in terms of what you just explained.
Yes. So you have to just accept for the time being this little equation. If I have two linear transformations, V, F and G, from V, F from V to W, G from W to P, all are finite dimensionals, okay? Then the matrix representing the composite, G composed F, so it is from A to C, alright? That is product of these matrices. Matrix from B to C of G, matrix from A to B, from A to B of F. Okay? That's that. So I'm just using this. So this is the matrix of F originally with respect to the standard basis. This is the change of basis matrix, which is the matrix of the identity with respect to U3 to this transposed basis. So their product will be the matrix of this composite, which is again F, but now from E4 to this transposed basis. So what's the end goal? What's the end? The end is, if you interchange the two rows of a matrix, it means that on the side of the codomain, you have interchanged those two vectors, got hold of a new basis, and multiplied the original linear transformation by the identity one. Okay? So you have just changed the matrix because the basis has changed. Okay? That's the whole story. Because the matrix has changed, because the basis has changed.
When multiplying matrix changes, when trying to read the multiplication of, you multiply by the off diagonal.
Not the off diagonal. I have interchanged the first and the third. Let's take that in that way. Okay? All right?
Excuse me, sir.
Yes.
Can you just link, so you see the whole transformation V to W, W to P.
Yes.
Yeah. Can you just link it to what you've done in terms of the identity matrix?
Yes, your G over here is nothing else but the identity linear transformation.
Okay.
Okay? So G composed F becomes F, and that's what I'm saying.
So the matrix A to C, which is G composed F.
Correct.
What is that now? Is it the?
Remember, identity linear transformation composed with anything. If it is composable, it gives back the same. So identity on R3 composed with F, it is F.
Okay. Yeah.
Yeah.
Okay. Okay. So the matrix from B to C, which is G, is your basically the identity matrix, that one. Is that 3 times 3 matrix?
Yes, but that is what? That is the change of basis matrix. Change of basis from the standard one to this transposed one.
Okay.
Yeah? So that matrix is this one. And this was the original one, as I said, from here. Okay?
Okay.
So F is represented by this. So this composed this means the composite is the matrix of the composite with respect to this basis and this basis. So the whole story is, therefore, multiplying on the left by this, interchanging two rows means multiplying on the left by this interchanged corresponding identity matrix, and that means actually that the linear transformation that was originally given is followed by the identity matrix, but the basis on the codomain has been changed, and hence the composite has a new matrix with respect to this new basis, and the basis of the domain was not changed. Okay? So that's what. Yeah.
So does it mean the number of rows for the identity should be the same as the number of rows for the matrix that you're multiplying on?
Obvious, right? Obvious, right? If it is an m cross n, you want the result to be m cross n. If you have to multiply on the left by anything, it must be an m cross n. So it has to be a linear transformation from Rm to Rn.
Okay.
Yeah.
So, what you're trying to get us to see is that when we interchange rows, basically
Yeah. When you interchange rows, it essentially means that you have changed the basis on the codomain.
Okay.
Yes.
Suppose then that one should be 2 by 4.
This one? This is a 2 by 4.
No, yes. I'm asking.
Yes, it is obvious.
This is an idea.
Yes, obvious. If this is a 2 by 2, this cannot be 3 by 4. It has to be a 2 by 4. Yes? Okay.
So, one more question. For the matrix, if you want to change maybe the second row with the third row.
So that means in the basis, you have interchanged the second and the third vectors.
So we still have to use that identity, the inverse of the identity.
So that means what would be its matrix? Its matrix would be with the second and the third row interchanged. That's it.
Okay. If I will there's always of mastering the matrices. If I repeat it, it will really allow, if I say 3 by 4 multiplied by 4 by 4.
No. Multiplication, the row operations do multiplications on the left, not on the right. Multiplication on the right means you are changing the column. You are changing the domain. The domain remains fixed. Okay? The basis of the codomain is just changed. Clear? Now let's look into this one. So suppose the second one. So suppose I want I want to multiply the second row by 2. So the rest remains to be the same. This has to be 2p, 2q, 2r, 2s, and this is x, y, z, t. So again, it must be a 3 by 3 matrix. And what should be the matrix? 1, 0, 0. Good. Correct. So then, what is happening on the basis?
They stay the same except the second one multiplied.
So, your E1, correct? Your E1 goes to E1. Your E2 goes to 2E2.
So you just write the coefficient. There's no need to write 0, 2, 0.
2E2 means actually 0, 2, 0. This goes to E3. Right? So the change of basis is now, so again the idea is the same. So you initially had so this was U4 and then you put R3, but here now my question is, what is the basis? What is the basis here? So what is the basis on this side? Whose thing is this?
2R, I say.
It is 2? No. So let's see. Suppose the basis is, so I'm doing this calculation. Suppose the basis is alpha, beta, and gamma. So E1, if the base is alpha, beta, and gamma, saying this, oh sorry, why did I remove this? Sorry. Let me, alpha, beta, gamma was scalars. So, suppose the basis is, say, let's say A, B.
So what is it?
Yeah?
So are these ABCs vectors?
Yes. That's why I made it bold.
No, I was asking about the two that you put there.
You told me.
There's a third row. E3. The linear transformation for E3 row, the third row, yes.
Where's E3?
No, I mean the coefficient.
Oh. Sorry. Thanks. So telling me this is actually what? Telling me that A, so this is the coordinates, right? So 1 times A plus 0 times B plus 0 times C is equal to E13. Right? What is this? 0 times A plus 2 times B is 2 times okay? Yeah. And similarly over here, 0 times A plus 0 times B plus 1 times C. So C is, so therefore your change to basis is still the same, right? Your change to basis, what is the problem? Okay? What's the problem? Okay, let's try it out again. I think, so I have R3, I have the usual basis over here, and I have the basis over here. Let's give this a name D. Okay? So, the change of basis matrix from to D. What is it? This is coordinates with respect to D of, okay, that's the first column. Coordinates with respect to D of E2 and coordinates with respect to D of E3. Okay? So, I know what is given this to me. Okay? So that means E1 is just A, because it is A, 1 times A, plus 0 times B, plus 0 times C. I'm just working this out because I messed up there. I made a mistake. E2, it is 0 times A plus, plus 2 times B plus 0 times C. Okay? So this comes to 2 times B. Right? So this tells me that 0, 1, 0 is 2 times B. Oh, why do I do this? Why do I bring this? So therefore, it tells me that B is half of, right? And similarly, E3, the coordinate is given to be this, so it is 0 times A plus 0 times B plus 1 times C, so which is C. So your basis is okay? So your basis is this. Clear? So I made up a mess there. So your basis is okay? So what's the goal then? Similar. Multiplying a particular row by a non-zero number lambda means you have actually changed the basis from the usual one, so that ith vector has therefore been multiplied by 1 upon lambda. Okay? So ith vector and the rest are kept same. So that's the new basis. Okay? So multiplying this, so multiplying a definite row means actually changing the basis. Okay? That corresponding vector has been multiplied by 1 upon that. Okay? Good. Now let's come to the last part of the story. So suppose I want to replace the third I want to make this the sum of So, what should be my matrix here?
Actually, the last one should, the last one should be, you have to add the
I'll give you the matrix.
One,
So what should be the first row? 1, 0, 0, good. Second row? 0, 1, 0. What should be the third row? 1, 0, 1. Right? Okay? So, what is the basis? So what is the new basis over here? That's my question. It's similar. Suppose it's A, B, C again. So it is telling me that here the coordinates of E1 with respect to A, or the coordinates of E2 with respect to that basis ABC is E2, so B is E2. Okay? C is E3. You see, it is telling me that 1 times A plus 1 times E3 is equal to E1, right? So that means A is E1 minus E3, right? So this changes to this one is a little bit complicated, but what do? What was you doing? You are replacing over here R3 by R1 plus R3. And what happened on the basis? R1, the first vector, is changed to the first minus the third. So over here, the ith basis vector become the ith minus the j. So you see now the row operations, therefore, all of them have this common feature. Row operations mean actually change of basis. So the moral is this. Start off with the usual basis on the domain and the codomain, go on changing the basis, okay, till the point you have a very nice echelon form for the corresponding representation of it. Okay? And now let's see how does echelon form? We already saw how echelon form actually tells us, immediately what is the kernel, what is the range of the matrix. Okay? Now what about, so it is actually multiplying by some linear transformations, right? So the whole point is therefore, so you had this linear transformation, you wanted to solve something like this. Okay? So this has a solution, this equation, so you wanted to solve. R1 become the ith